Good morning, students. In the last class, we studied about Snell's law, which states that the ratio of the sine of angle of incidence to the sine of refraction is a constant, and this constant is known as refractive index, which is denoted by small n. Today we will study about refractive index. Now we know that the speed of light changes when it moves from one medium to another medium. As a result, refraction takes place. Now, the amount of change, means by how much the speed of light is changing, depends upon the property of the medium, which is known as refractive index. So, refractive index determines by how much the speed of light will change from one medium to another medium. Now we all know that light travels fastest in vacuum. And what is the speed? That is 3 into 10 to the power 8 meters per second. In air, again, the speed of light is slightly less than that of vacuum. So we consider the speed of light in air also the same as that of vacuum, that is 3 into 10 to the power 8 meters per second. Now the value of the refractive index for a given pair of media depends upon the speed of light in the two media. So what will be the refractive index for a given pair of media will depend upon the speed of light in the two media. For this, let us consider the two medium. The first medium be air and the other medium be glass. Now consider a ray of light moving from medium 1, that is air, into medium 2, that is glass. Now let the speed of light in medium 1 be V1 and that in medium 2 be V2. So the refractive index of medium 2 with respect to medium 1, I repeat, the refractive index of medium 2 with respect to medium 1 is given by this N21. Refractive index of medium 2 with respect to medium 1, which is given by the formula speed of light in medium 1 divided by speed of light in medium 2. And we have taken the speed of light in medium 1 as V1 and speed of light in medium 2 as V2. Similarly, the refractive index of medium 1, just again the reciprocal of this, with respect to medium 2 is given by N12, which is equal to speed of light in medium 2 divided by speed of light in medium 1, which is equal to V2 by V1. Now these two types of refractive index, when we are considering about the two medium, they are called relative refractive index. Now let us talk about another term which is known as absolute refractive index. So what is absolute refractive index? It is defined as the ratio of the speed of light in vacuum. Okay, so here one will be the speed of light in vacuum or air to the speed of light in any medium. It can be any other medium. So it is, and again it is denoted by N. So refractive index, absolute refractive index is also known as refractive index. We can, when we talk about refractive index, we talk about absolute refractive index. So it is given by the formula speed of light in air or vacuum divided by speed of light in any other medium. Now we know that. Now we denote the speed of light in air or vacuum by C. So N is equal to C by V, where V is the speed of light in any other medium. Now what is the speed of light in air or vacuum? That is 3 into 10 to the power 8 meter per second. Now what do we find here? That it is the ratio of the speed of light. So it is a pure number, means it has no unit. You always know that ratio, whenever there is a ratio, it has no unit. So refractive index has no unit. Now absolute refractive index of a medium is always greater than 1. Children, remember this, that absolute refractive index of a medium is always greater than 1. Why? Because we know that the speed of light in vacuum or air is the greatest. Okay, light travels fastest in vacuum or air than any other medium. So whatever medium you take, C will be always greater than V. And when the numerator is greater than the denominator, your answer is always greater than 1. So absolute refractive index of a medium is always greater than 1, whereas relative refractive index of a medium may be less than 1. Now another term which we will be studying today is optical density. Now what is optical density? It is the ability of the medium. It is the property which determines the ability of the medium to refract light. Means which medium refracts light by how much. So that is known as optical density. It is directly proportional to the refractive index of the medium. Means more the refractive index, more is the optical density. The medium with larger refractive index is optically denser than the other. And we know that the speed of light in denser medium is less than the speed of light in the rarer medium. So more is the refractive index, less is the speed of light in the medium. It is just inversely proportional. The speed of light is inversely proportional to the refractive index. More is the refractive index, less is the speed of light. More is the refractive index, more is the optical density of that medium. Okay. Now another term which you all have studied till now is mass density. Mass density is simply mass per unit volume of the substance, which you all have studied in your previous classes also. So optical density is the ability which determines, it is that property that determines the ability of the medium to refract light. More the optical density, more is the refractive index. Now another thing which we will study is factors on which the refractive index of a medium depend. There are 3 factors on which the refractive index of a medium depend. Number 1 is the nature of the material of the medium. Second is the density of the medium. Just now I told you, denser the medium means more is the optical density, more is the refractive index. Then it also depends on the nature of the material of the medium through which the light is passing, and color or wavelength of the light. It is minimum for the red light and maximum for the violet light, which we don't have to go in detail in this class. Now another topic which we will be dealing now is refraction through a rectangular glass slab. Now another topic which we will be dealing now is refraction through a rectangular glass slab. So let the two medium again be here, air, and this is glass. Now let us assume that this ABCD is a rectangular glass slab. Now let incident ray EO traveling in air strike the glass slab at an angle of incidence I1. Okay. Now after refraction, the ray bends towards the normal. Why is it bending towards the normal? I have already told you that when the light ray travels from rarer to the denser medium, it bends towards the normal. So it is bending towards the normal. Now this refracted ray, O dash, this is the refracted ray which is making angle I2, okay, with the normal M dash. At this point again, now what is happening, this O dash, now since it is refraction is taking place and it is a rectangular glass slab, so what will happen, the light will come out, it will emerge out of the glass slab. Now what will happen, now it is coming out from glass to air, so it is moving or traveling from denser to the rarer medium, so it will bend away from the normal. Okay, so this O dash H. This O dash H is the emergent ray which is coming out of the rectangular glass slab. So for incident ray EO, O dash is the refracted ray, and for this emergent ray O dash H, O dash acts as the incident ray. So this ray is known as O dash H is known as emergent ray, and this angle is known as angle of emergence. Now when you just extend this incident ray, you will find out that this incident ray EO is parallel to O dash H. Now why this happens? When a ray of light falls on a glass slab obliquely, it emerges out of the glass slab parallel to its original direction of propagation. So its original direction of propagation was this, and now it is coming out or emerging out of the glass slab parallel to this incident ray. But what do you find? That there is a slight shift in the path of this incident ray, and this shift is known as lateral shift or lateral displacement. So this JK is the lateral shift or lateral displacement. One thing also you remember, children, that angle of incidence and angle of this is angle of emergence. Okay, so angle of incidence and angle of emergence is always equal. Then only they are coming parallel to each other. Now the question is, why incident ray and emergent ray are parallel to each other? This is because the opposite faces of this rectangular glass slab are parallel to each other. Okay, so you will find that this angle I and angle E are equal to each other. Now what is lateral shift or lateral displacement? The perpendicular distance between the direction of original path of incident ray and the direction of emergent ray coming out of a glass slab is called lateral shift or lateral displacement of the emergent ray of light. So children, two things you should remember for the refraction through a rectangular glass slab. First, the incident ray and emergent ray of light are parallel to each other, and number two, angle I is equal to angle E. Now we will start with another topic, that is refraction by spherical lenses. Now what is a lens? It is a transparent medium bounded by two refracting surfaces. Okay, so what is a lens? It is a transparent medium bounded by two spherical refracting surfaces. Of these two refracting surfaces, one may be spherical and it may have two spherical refracting surfaces, or one spherical and other plane. A lens may have two spherical surfaces bulging outwards, and that is known as double convex lens, or it is simply called a convex lens. So this figure which you are seeing, it is a convex lens. Convex lenses are also called converging lenses. Okay, it is thicker at the middle and thinner at the edges. Why are they called converging lenses? Because they converges light. You can see from here that when parallel beam of light is passing, it is all rays of light after refraction is converging at a particular point. That is why it is known as converging lens. Similarly, a double convex, this is known as concave lens. Okay, so this is bounded by two spherical surfaces curved inwards. It is curved inwards. So this is it is known as double concave lens or simply concave lens. What do you find by seeing this figure? That it is thicker at the edges and thinner in the middle. These type of lenses are called diverging lenses, because you can see from the figure that these rays of light, the rays of light in these lenses after refraction are getting diverged. Okay, so that is why this concave lens is also known as diverging lens. Now let us understand some terms which we will be using in this chapter while making the ray diagrams. Now this is the principal axis. So what is a principal axis? It is an imaginary straight line passing through the two centers of curvature of the lens. Now why there are two centers of curvature? This is because you know that this is a sphere, first sphere, and this is the second sphere. And these two, it is made up of two refracting surfaces bulged outwards. So it is a part, this lens is a part of this sphere and this lens is a part of this sphere. So both spheres are having their own centers of curvature. So these two centers of curvature are denoted by C1 and C2. So centers of these spheres, of which this spheres forms a part, are called the center of curvature of the lens. It is the center of curvature of the convex lens. So principal axis is the imaginary straight line passing through the center of two centers of curvature of the lens. Now optical center. This is the optical center of a convex lens and concave lens. Now what is this optical center? It is the central point of the lens. This is the central point of the lens through which rays of light pass undeviated. Here there is no deviation taking place at the optical center and it is denoted by O. Now what is aperture? This is the effective diameter of the circular outline of a spherical lens. Now principal focus. This is the principal focus of a convex lens. This is the principal focus of a concave lens. Now what is that? It is a point on the principal axis of a lens where all rays of light parallel to the principal axis meet or appear to meet. Here it is appearing to meet. Here it is actually meeting after passing through the lens. This is called principal focus and it is denoted by capital F. A lens has two principal foci, f1 and f2. Because it has two spherical spheres, so there are two principal foci which is denoted by f1 and f2. Now what is focal length? The distance between the principal focus from the optical center, okay, is called focal length. So in case of convex lens, you can see this is the focal length. It is towards the right. We take it towards the right. And in case of concave lens, we take it towards the left. So students, for today this, write down the notes in your copy. Next day we will study about the image formation. Thank you.